Hello wonderful person, this is Anton, and in this video we're going to be discussing a fascinating new experiment that might slightly change how we think about the fabric of space-time, the reality, and specifically the nature of time itself. And that's because for a relatively long time, physicists struggled with a kind of a major contradiction. Our daily reality of life shows time as something that flows from the past into the future. Or basically it shows us a kind of a arrow of time. But our deepest equations of the universe don't actually include this external ticking clock and do not require any arrow of time to explain the universe we live in, which by itself creates a bit of a contradiction between what we're observing and what's being theoretically proposed. And so extremely recently, a team of scientists led by Professor Giovanni Bortini at the University of Birmingham created what they now refer to as a kind of a mini-universe, a tiny representation of the universe inside the laboratory setting that tries to tackle this exact problem and tries to explain this idea of time in ways we can maybe understand. But in this case, they did not create stars or galaxies, they created something much smaller and much colder, and something that's been used in a lot of experiments before. They used a Bose-Einstein condensate, something we're going to briefly discuss in a few seconds. And so here, by observing how this tiny system changed over time, and by measuring the flow of time inside of it, and in this case without using any actual clock, they were sort of able to show that time might be some kind of an emergent property resulting from the system's internal changes. And so just to kind of make sense of all of this, let's first discuss some of these individual concepts and then basically find out what this experiment shows us. But before we dive into this mini-universe, we need to understand these two main concepts, Bose-Einstein condensates and the idea of entropy. And so what exactly is a Bose-Einstein condensate, very often referred to as a BEC? Well, scientists sometimes refer to this as the fifth state of matter. So basically not liquid, not gas, not solid, and not plasma, but a BEC state. And this is when you take a gas of certain atoms, in this case very often rubidium-87 atoms, and cool them down almost to the absolute zero. And well, at this point, something strange starts to happen. The atoms lose their individual identity and begin to overlap, merging into a single superatom, or to be more exact, a giant quantum wave, which then allows scientists to see quantum mechanical effects by physically observing them with the equipment in the lab. This is something that has been recreated many times and was even created on the International Space Station a few years back. But the second concept here is entropy, and that's maybe a little bit more difficult to explain, even though it's basically just chaos or disorder. But entropy is actually the measurement of this disorder that technically measures the spread of energy inside a system. And well, according to the second law of thermodynamics, entropy in an isolated system almost always increases over time. And it's really this increase in disorder that seems to be the only thing in fundamental physics that gives us a very specific direction, or this arrow of time. Or basically in physics we can define time as a direction of increase of entropy. Although my apologies for not really explaining entropy very well, because it is a relatively complex topic that basically deserves its own video. That will probably come out really soon because I've been working on this for several years now. But for now though, let's I guess move on. Let's discuss the problem of time. Or basically, why did scientists even need this mini-universe to study this? Well, it's really because of something referred to as Wheeler-DeWitt equation, which is a major part of quantum gravity and tries to combine the rules of the very small things, or the quantum mechanical things, with the rules of something very large, such as black holes or other objects from the general relativity. And the problem here is that this equation describes the entire universe as a kind of a stationary, unchanging state, where time doesn't actually exist as any kind of a parameter. As a matter of fact, as you can see in this equation, there is no t, no time at all. And if the universe is everything there is out there, there cannot be any clock outside of it in order to tell it how to change. Or just to rephrase this, if this describes the actual universe, then where exactly is the time? It cannot just exist outside of it. Which leaves scientists with a huge question. If the universe has no built-in clock, how do we actually get the idea of before and after that we basically experience every single day? And that's why this mini-universe experiment was designed. And so to test this, the Birmingham team created a simplified version of the universe by making a cloud of approximately 24,000 rubidium atoms behave in a somewhat unusual way. And they did this by trapping them using lasers and magnetic fields. That's basically the machine you see in this picture. And then they used a very thin barrier of light to divide this cloud into two separate parts. A kind of a bright sector that they were able to directly observe and measure, and the dark sector that remained unobserved. And while the atoms in this particular universe were able to move back and forth across this barrier, allowing things to change just a little bit. And as atoms moved between the bright and the dark sector, the overall volume of these regions would expand and contract. Or to be more exact, the size of the bright region would change just a little bit. And this expansion and contraction was actually kind of mimicking the idea behind the Big Bang, followed by a kind of a big crunch, or the expansion and the contraction of this mini-universe. In other words, by literally doing absolutely nothing, researchers made this particular mini-universe behave in a very unusual way that we kind of observe in the real universe as well. But importantly, researchers wanted to do one thing here. They actually wanted to see if they can maybe describe the order of events in this system, or how the events happened in this bright sector. For example, what happened first, what happened next, without looking at the external clock in the laboratory, and by using the system itself. And for this, they used the idea of entropy. And so by measuring the dispersion and the number of atoms moving between the bright and dark sides, they created a kind of an entropic time, with this graph basically showing us how this entropic time seemed to progress. And so what exactly did all of this help us discover? Well, here the results were actually kind of remarkable. First, they found that this entropic time was an extremely robust way to track the progression of events inside this mini-universe. In other words, by using the idea of entropy, it was possible to kind of keep track of things even without an external clock. With the main discovery suggesting that time is indeed internal, or basically the experiment proves that time can be defined by the internal changes of a system and not an external clock, and proving that the arrow of time is real after all. Because even as this mini-universe expanded and contracted, going through these Big Bang, Big Crunch cycles, the entropic time only moved in one direction and gave the entire system a clear arrow from past to future. But there are also some additional discoveries that are maybe just a little bit surprising and do have some implications for our universe. First, they noticed that the entropic time didn't always flow at the same rate. It seemed to flow faster when entropy was being exchanged quickly, and even completely stopped if no changes were happening. And in their experiment, if the system reached a state referred to as the heat death, where everything becomes basically more or less uniform, time effectively ceased to exist. Or basically the whole universe kind of froze in time. Now exactly what this means for our universe is of course still kind of debatable, but this is definitely an intriguing observation. And there's also discovery in regards to quantum consistency. Here the team was even able to write a version of the Schrödinger equation, the fundamental equation from the quantum physics, using this internal entropic time instead of normal time. And it actually successfully predicted how the atoms would behave. In other words, even the quantum effects inside the system seem to behave in a very similar way how we expect them to behave in the real universe as well. But I guess the main question is, so why is this important? Or why spend so much time and effort to measure time without a clock? Well, the main reason is that this experiment provides a controlled testbed for the most difficult theory in cosmology. And that's because for decades ideas about how time emerges was mostly based on mathematical propositions and were more or less impossible to test. Mostly because we cannot just go and observe things from outside of the universe and cannot test anything in that way. But it also suggests that our idea of time or our experience of time is not some kind of an absolute and is not something that's dictated by something else from outside. As a matter of fact, it's not even some kind of an underlying property of the universe, and instead seems to be a relational property. Or basically something that emerges because different parts of the universe are interacting and exchanging energy and information. And if the universe was very simple and nothing actually happened in it, or basically if nothing ever changed, time would not be just slowing down or standing still, it would simply not exist. Without entropy, there would be no arrow of time. With this experiment supporting the idea that the universe is essentially a kind of a closed quantum system. A system where the total state does not seem to change, but for things inside this system, time then appears to exist because individual subparts of the system start to interact and start to exchange energy and entropy. Or just to rephrase this in, I guess, more understandable terms, it's kind of like being inside a movie where the entire film reel already exists all at once and has already been made. But as the light passes through individual frames in the film, we then start getting a kind of a story with the beginning and the end visible to the audience. And so definitely an exciting experiment and some really intriguing implications. But naturally, this approach of using mini-universes can also help us discover and understand other unusual principles as well. For example, studying exotic objects like black holes, or even trying to figure out the exact conditions that existed during the actual Big Bang, could possibly also be explored by using these tiny mini-universes with Bose-Einstein condensates and using setups that are not so different. In other words, all of this shows us that we don't really always need these massive telescopes like the James Webb to try to understand the cosmos and to try to figure out our place in it. Because sometimes the secrets of the entire universe can also be discovered in a tiny cloud of atoms, cooled down to some of the most extreme temperatures. But because this is such a complex research and because there are still a lot of unanswered questions, there's obviously still a lot we don't really understand about quantum mechanics, and more importantly, how gravity seems to fit into this story as well. Which means that we'll definitely come back and discuss this more in some of the future videos. And on that note, thank you for watching, subscribe, come back tomorrow to learn something else, support this channel on Patreon where you can find additional videos without any ads and can DM me directly, or by joining a channel membership that grants you early access. You can also support this channel by buying the Wonderful Person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.